gonna talk about rearrangement of carbocation. So rearrangement of carbocation. First of all, let's look at alpha beta shift, or we also known as 1-2 shift. So what is alpha beta shift? Let's take first example. We have first hydride shift, H shift. So how does hydrogen shifts? Let's say we have an CH3, CH2, then CH2 plus. So that hydrogen we have here, hydrogen we have here, then gonna shift on first, second hydrogen shifts gonna shift on first carbon, CH3, CH plus, and CH3. Now what does it happen? CH3 we have CH, we have P loop, sp2 sp3 loop, and hydrogen is attached over here. Then we have C carbocation, hydrogen and empty p orbital. So this hydrogen shift here. How does it shift here? We have CH3, CH, this sp2 lobe, sp3 lobe, hydrogen we have, and we have C carbocation, H and H. So this hydrogen gonna overlap with this first number carbon. So CH3, CH, CH2, hydrogen, then delta positive and delta positive. Now CH3, CH plus, and CH2H. Hydrogen shifts here finally, and we get positive charge over the second number of carbon. So actually here it is partial double bond formation. Here there is a partial bond formation, not double bond. It is partial bond formation. So let's see some example. First of all, let's see why does carbocation shifts. Carbocation shifts because whenever there is a free carbocation, the carbocation which is free, that has to be rearranged in order to get the stable carbocation. So in the world, everyone wants to be stable. So carbocation also wants to be stable. But when the carbocation wants to be stable, it has to be free first. So it is a reaction intermediate, which reaction intermediates comes in various reactions. So whenever the carbocation is free, it gonna rearrange by itself. It do not need any external energy. That we're gonna look in examples when we doing some problems related to some equations when the carbocation exists. We're gonna look a lot of equation where carbocation rearrange. So let's take first example. We have CH3, CH3 and CH2 plus. So first of all, what will happen? This hydrogen gonna interchange with the next one, C plus, CH3, and hydrogen will come shift on the first carbon. From second to hydrogen will shift on the first carbon. Now in second case we have CH2 positive and H. Hydrogen gonna shift from here to here. Why? Because after shifting this hydrogen, the carbocation we are getting is more stable because it is 3 degree carbocation. Initially it was 1 degree, now it is getting 3 degree. And the which hydrogen shift, the hydrogen which just next to that carbocation, is only gonna shift. Not 1-3 shift takes place, only 1-2 or alpha beta shift take place. Third, we have CH3, CH, CH3 and CH2 plus. Now first of all we know that this shift gonna take place. This carbocation will go here or hydrogen will go there. So what will happen? First we have CH3, CH3, CH plus and CH3. Now again there is a possibility of shift one more hydrogen, because after shifting the hydrogen the carbocation will is getting are more stable, relatively more stable. So the final carbocation we are getting CH3, C plus, CH3 and CH2 and CH3, because the final carbocation is more stable than second one and second one is more stable than first. So in every step there should be more stable. It won't shift if it is 2 degree to going to 2 degree, 3 degree going to 3 degree, or 1 degree is going to 1 degree. It won't shift. It will shift when 1 degree is going to 2 degree, 2 degree is going to 3 degree, or 1 degree going to resonance, means numeric effect. We're gonna look at more examples so you will understand it more. Let's say we see the question number 4. Question number 4. We have CH3, CH. That question we have seen. Let's look at the next question. We have this carbocation, the hydrogen is there and this double. So what will happen? This hydrogen will shift. Not the, if we have two hydrogen, they means hydrogen 1 and hydrogen 2. So hydrogen 1 will shift. Why? Because after shifting the hydrogen, the carbocation is getting resonance stabilized. It is in conjugation with double bond. So here it is carbocation shift, or we can say hydrogen shift, not carbocation rearrangement or a hydride shift simultaneously. Fifth, we have pH, CH, CH3 and CH2 plus. So in this case, the carbocation shift, it will become pH, C plus, CH3 and CH3. Now it is more stable than the previous one. Sixth case, let's see, pH, CH, CH3, CH, CH3, CH2 and CH2 plus. Now it will be pH, CH, CH3, CH plus and CH3. First it will shift. Now next it may also shift next time, because it was 1 degree, now it is 2 degree. Now by shifting one more time it will become 3 degree. So each and every step should be profitable. It is 3 degree, then only it shift, otherwise it won't shift. Each and every step should be profitable. We can also write each and every step should be profitable for carbocation, we can say. Let's shift more. We have this carbocation over here. So it's gonna shift either to carbon 1 or carbon 2. It's gonna shift on carbon 1 because here it is stabilized by plus M effect of oxygen. Eighth, again if oxygen, there was a nitrogen instead of oxygen, so it's gonna also shift there because nitrogen is also having lone pair which can also donate to the carbocation. 10, we have CH3, O, CH2 and CH2 plus. Yes, it will gonna shift because it is getting stabilized by CH plus and CH3. Now let's look 11th, pH, CH2 and CH2 plus. Yes, it will gonna shift pH, CH plus and CH3 because it is getting stabilized by the resonance. 12th, CH3O, CH2, CH plus. So where the carbocation will gonna shift? Yes, carbocation is going to shift because this part is stabilized by the resonance. Here carbocation will come and yes, if there is a carbocation here, shift here, it will go in resonance and it will reach up to here, which is stabilized by the lone pair of oxygen. again this carbocation, it will go up to here and it is stabilized by the lone pair of oxygen. So it is actually CH3O CH plus CH2. Yes, it will shift. 13. Yes, it will shift. Now I am writing some questions and you need to answer. 14. 15. 16. Just pause the video and try to answer by your own. Now let's write the answers there. 14th, yes, it's gonna shift. It's gonna shift because it is now 1 degree. After shifting, it is getting 2 degree. And one more shifting, it is getting 3 degree. Right. Now this is also gonna shift because this is going to take part in dancing resonance. Yes, it's also gonna shift because it is stabilized by the resonance. Let's dig some more problems. Yes, it's gonna shift carbocation. Now one more shifting is possible, 2 degree to 3 degree. 18th, let's see. Here it is carbocation. Yes, it's gonna shift because here dancing resonance cannot take place, so it will be stabilized by the resonance, or we can say it is now aromatic. Now 19th problem, that is quite interesting shift. We have pH, and we have carbocation here. So first carbocation will shift pH because it is stabilized by 1 degree to 2 degree. Then it will gonna shift because it is stabilized by 2 degree to 3 degree. Now it again gonna shift because again it is stabilizing by resonance. Yes, one more shift because it is again stabilizing by 2 resonance, 2 phenyl groups nearby carbocation. So how many shifts are there? We can say there 1, 2, 3, 4. 1, 2, 3, 4 shifts are there. 4 shifts. Next, 20th problem. 20th problem. We have this carbocation. Yes, it's gonna shift because it is making anti-aromatic. When it's gonna shift to the next one, it will make next one aromatic and it will become non-aromatic. 21st. Carbocation is here. Yes, it's gonna shift because it is getting more number of alpha H. Here alpha, both are 3 degree, but here alpha H is 1, 2, 3, 4, 5. But here alpha H is 1, 2, 3, 4, 5, 6, 7. So yes, it will shift. 22. Carbocation is here. Yes, it will shift because again more number of alpha H we will getting after shifting. 23. CH2 plus CH2 as CH3. Yes, it is again gonna shift because of plus M effect of sulfur. Plus M effect of sulfur. 24th. Yes, is again gonna shift because of resonance stabilizing. 25th. Yes, is again gonna shift because of more number of alpha H. Now that was all about hydride shift. Now let's talk about phenyl shift. Second shift is phenyl shift, or we can say pH shift. So how does the phenyl shift take place? It is also 1-2 shift or 1-2 shift on alpha beta shift. Now how does phenyl shift take place? Suppose we have phenyl, C phenyl, CH2 positive, Again we have this. So out of these three phenyl, what happens? For phenyl has to be shift because it will generate more number of carbocation, more stable carbocation. pH C, pH CH2. That's how this gonna make bond here, and it will be that type of intermediate. So finally the product will be pH C, pH plus CH2 and pH. Next we have alkyl shift also. Third is alkyl shift. If we try to shift the alkyl, that is also 1-2 shift on alpha beta shift. So we have CH3, C, CH3, CH3 and CH2 positive. So if we have no option to shift the CH3 group only, because that's the only way to get stable product. So we have CH3, C, CH3, and we have delta positive, and here we have delta positive. Now it will gonna form the CH3, C carbocation, CH3, CH2 and CH3. Right, that's how the carbocation gonna form. And now let's solve for reversible reaction. Why I am writing reversible reaction? Because in reversible reaction we shift the carbocation. Carbocation shifts where it is getting more stable. What does it mean? Let's say we have a reversible reaction. In the question we will be knowing whether the reaction are reversible or not, or we will be judging the reactions on the basis of its mechanism. Let's say we have CH2 plus. Now we have three options here. We can shift hydride, methyl and phenyl. So what we're gonna shift? We're gonna shift hydride, because after shifting of hydride we are getting most stable carbocation. If we would have shift remaining two, one of them, right? If we shift CH3 we will getting lesser stable carbocation. If we shift phenyl we will be getting lesser stable carbocation. Next we have CH3, CH3 and CH2 plus, and we have this methyl. So which gonna shift here? We again have to shift some compound, some group. After shifting the bulky group, the tertiary butyl group, we gonna get the most stable carbocation. We're gonna get the most stable carbocation because it is a 1, 2, 3, 4, 5, 8 alpha H. If we would have shifted a methyl carbocation, now we are going to shift alpha H as 5 only. So this is wrong, this is right. Right. Third, CH3, CH3, pH and CH2 plus. Here we have to shift methyl only, because after shifting the methyl we are getting more stable carbocation. Now here why we are shifting methyl only? Why we are shifting? Because we are getting more stable carbocation, and the reaction is reversible. The reaction has to be reversible. When the reaction is irreversible, we're gonna see that problem also. CH3 and pH. So here which gonna shift? Methyl gonna shift because of it is will get the more stable carbocation by the phenyl resonance. Fifth we have the methyl shift, the ethyl shift, because methyl will have more number of alpha H after shifting. Sixth, we have this group. So if it is gonna shift, we know the more substituted group gonna shift, because after shifting that we will getting more number of alpha H. That was all when the reaction was reversible. The most important, when the reaction is irreversible. When the reaction is irreversible, we don't have to judge by the stability of carbocation. We judge it by the migrating migratory aptitude. What is migrating? First hydrogen will shift, then phenyl will shift, then alkyl group will shift. This have to be the order when the reaction is irreversible. Let's say we have a irreversible reaction. Let's say we have a irreversible reaction. So in irreversible reaction A, we have CH3 CH plus H and CH3 CH2 plus. So here hydride has to be shift because the migrating aptitude of hydride is more than methyl. B, we have CH3 C CH3 CH2 plus, and we have a cyclohexane benzene group, phenyl group. Now here the phenyl has to be shift because its reaction is irreversible and migratory aptitude of phenyl is more, so phenyl will shift. Phenyl will shift. C, we have CH3 CH2 plus. Which group gonna shift? 3 degree group gonna shift because better electron donor are better migrator. Better electron donor are better migrator. So which are better electron donor has to is better migrator. Like we have to compare migratory aptitude, which is migrating more. A, we have hydrogen, deuterium and tritium. So we know hydrogen has more migrating aptitude than tritium due to its weak bond. Hydrogen is a weak bond with carbon, so hydrogen will shift first. B, we have CH CH2 CH3 CH3 and CH3 CH3 and CH3. So which is more electron donor with window has to be more migrator. C. Now we have phenyl groups. Here we have methyl and we have OCH3 group attached over. So third group gonna shift first migrating aptitude order because it is more electron donor because plus M. It is getting plus M, it is getting plus H. So plus M is more dominating than plus H. Next we have benzene, then we have NO2 group attached nitrate, then we have CH3. So it is first, it is second and it is third group. E group we have CH3 and here we have CH3. So second is more because it is having less steric hindrance. What do we mean by less steric hindrance? Let's say we have shifting. We have CH3 C CH3 CH2 plus, and we have this methyl and CH3 group. So when this group gonna shift, so this group gonna hinder it. This group gonna hinder while making that bond. So this group will hinder. So steric hindrance will occur. Now in next video we're gonna see in ring. We have seen right now in without ring. Now we will see ring expansion or ring contraction.